Artificial intelligence has evolved from a research niche to a core business competency. But the field moves fast. Terminology often outpaces understanding, leading engineers and product managers to conflate the underlying language model with the overall autonomous system. AI fluency is a matter of understanding the architecture. These terms are more than a vocabulary list. They are components in a system schematic. We are going to build a production-ready autonomous agent from scratch, defining the exact terminology needed at every layer of the modern AI stack. Approaching these concepts as an engineering blueprint allows us to move past consumer hype and design robust, multi-step enterprise solutions. The baseline of our stack is the foundation model, a large pre-trained model that serves as a reasoning engine. When text enters the system, the model breaks it down into tokens. In English, one token represents roughly 3/4 of a word. The model's capacity to store and apply knowledge is determined by its parameters. These numerical weights dictate whether a model is small enough to fit on a mobile phone or large enough to require cloud infrastructure. Every model is limited by its context window, the maximum number of tokens it can process in a single interaction. If you feed a 150,000 token contract into a model that can only handle 100,000, the system silently truncates the excess. Every time the model generates an output from a new input, it is performing an inference. Training is a one-time cost, but in production, we measure success by the speed and cost of these inferences. A foundation model running single-turn inferences is powerful, but it is stateless, isolated, and rigidly limited by its token capacity. This isolation is a design choice. Language models effectively have short-term memory. They hold information for the current session, but they lack a built-in long-term memory to retain data across future interactions. Relying solely on internal parameters leads to hallucination. The model might confidently claim Brazil won the 1942 World Cup, despite the fact that the tournament was never actually held that year. We solve this with retrieval augmented generation, or RAG. This architecture provides external memory by converting documents into embeddings, numerical representations of semantic meaning. These embeddings are stored in a vector database. This allows the system to perform semantic search, finding items that are conceptually similar to a query, even if the keywords don't match exactly. When a query arrives, the system retrieves the most relevant content and injects that content directly into the model's prompt as context. We call this grounding. The model's response is now constrained by verifiable data rather than its own internal patterns. Externalizing memory removes the guesswork, turning the probabilistic generator into a robust retrieval system grounded in real-world facts. A retrieval system is still just a chatbot. To take action, we need an AI agent. This system uses the model as a reasoning engine to pursue goals through an agentic loop: plan, act, observe, and refine. For complex tasks, we move to a multi-agent system, where specialized agents collaborate on a shared goal under the eye of an orchestrator. The router agent serves as the entry point. It examines the query and directs traffic to the correct specialist without answering the question itself. The planner agent then takes the high-level goal and decomposes it into concrete, sequential subtasks. Finally, the executor agent receives those tasks and executes the steps using the specific tools at its disposal. This is tool use, the ability to call external APIs, to execute custom code, or to query databases. This is what allows an agent to interact with the digital world. Agents use the React framework to interleave this reasoning with action, observing the results of a tool call before deciding on the next step. To make these connections scalable, we use the Model Context Protocol, or MCP. It allows agents to dynamically discover and connect to tools without hard-coded integrations. Combining orchestration, loops, and external tools gives the AI system the limbs necessary to execute complex workflows autonomously. An efficient architecture doesn't require a massive model for every single task. For low latency or on-device tasks, we use small language models. These SLMs offer privacy and speed for simpler operations like summarization. For more complex reasoning, a mixture-at-expert architecture activates only the relevant subset of its parameters for a given query, keeping inference efficient even with a high total parameter count. When the data is visual, we integrate vision language models to process images and text simultaneously. Robust architecture is about matching the exact model size and modality to the specific requirement of each node in the system. Once built, we shift into a production context to manage enterprise realities. We monitor latency, the time delay between a request and response. In real-time applications, every millisecond counts. We also track throughput, which measures the total capacity to handle parallel requests across the infrastructure. Scaling safely requires AI governance, a framework of policies ensuring the system remains responsible. Governance is enforced through guardrails. These validation layers monitor agent behavior and block prohibited actions, like an unauthorized database deletion. For high-stakes operations, we use a human-in-the-loop pattern, requiring manual authorization before a final action is taken. This architecture evolves the model from a stateless text predictor into a governed system capable of taking real-world action. True AI fluency is understanding where every component lives in the stack and how those components interact to achieve a goal. Building with this technical architecture is how we engineer AI solutions that actually work in production.